What happens inside your body when you break a bone? One second, that is all it takes. And then, something inside you breaks. A bone strong enough to carry your weight, protect your organs, and hold your body together suddenly splits. But the fracture is only the beginning. A broken bone may look like an injury, but inside your body it is a construction site, a rescue operation, and a biological miracle happening all at once. Today, we go inside the human body to watch a broken bone heal. This is Innerium, the science inside you. The moment of fracture. Bone is not dead material. It is alive. It has blood vessels, nerves, and living cells. It is constantly being repaired, reshaped, and renewed, even when you feel nothing. But every bone has a limit. When a force becomes too strong, when pressure arrives too fast, or when the angle is wrong, the structure begins to fail. Tiny cracks can appear inside the bone. If the force continues, those cracks spread through the hard outer layer and deeper into the internal structure. In a fraction of a second, the bone gives way. This is the moment of fracture. Inside the body, the solid structure of the bone separates. The protective outer membrane around the bone, called the periosteum, can be stretched or torn. Small blood vessels break open. The tissues around the fracture are disturbed. The first alarm comes from pain. Pain is not just suffering. Pain is information. It is the body's emergency message. Stop moving. Protect this area. Something is damaged. The sharp pain of a fracture often comes from tissues around the bone, especially the periosteum. The periosteum is a thin, sensitive layer covering much of the bone surface. It contains nerves and blood vessels. When it is torn, stretched, or crushed, those nerves send urgent signals through the nervous system toward the spinal cord and brain. In milliseconds, the brain receives the warning. Your nervous system is trying to stop you from making the injury worse. When a bone breaks, unnecessary movement can disturb the broken ends, irritate tissue, and increase damage. So the body makes the area painful, not to punish you, but to force you to protect it. At the same time, blood leaks from damaged vessels in and around the bone. Within minutes, this blood begins to clot. This is called a hematoma. A hematoma is a blood clot around the injury. It helps stop bleeding, traps chemical signals, attracts immune cells, and marks the place where reconstruction must begin. From this moment, the fracture becomes a biological construction zone. But before the bone can rebuild, the body must first clean the battlefield. Inflammation is not the enemy. After a fracture, the body does not begin by building new bone. First, it creates inflammation. Inflammation is not a mistake. It is the body's first organized response to injury. The hematoma contains blood cells, proteins, signaling molecules, damaged tissue, and fragments from the trauma. Before rebuilding can begin, the body must deal with this damage. So, immune cells arrive. Some of the first are neutrophils. They react quickly to injury and release signals that attract more immune cells. Then, macrophages arrive. Macrophages are extremely important in fracture healing. They clear dead cells and damaged tissue, release signals that guide repair, and help move the body from inflammation into rebuilding. This is why inflammation must be balanced. Too little inflammation and repair may not activate properly. Too much inflammation, or inflammation that lasts too long, can interfere with healing. The body has to create enough inflammation to start repair, then slowly calm it down so rebuilding can begin. At the same time, the area swells, blood flow changes, fluid moves into damaged tissue, immune cells enter the area, chemical signals increase local activity. Swelling can feel like the enemy, but in the early stage, it helps create the repair environment. Pain also continues because surrounding tissues are inflamed, under pressure, and chemically irritated. The nerves around the injury become more sensitive. This sensitivity protects the fracture. It tells the body not to move the area too much, not to put weight on it, and not to disturb the repair site. The broken ends of the bone need stability. The body can rebuild bone, but the pieces must stay close enough, stable enough, and aligned enough for repair to work. This is why casts, splints, plates, screws, rods, or external fixators may be used. They do not heal the bone by themselves, they create the conditions that allow the body to heal it. Inside the fracture, the hematoma becomes more than a clot. It becomes a signaling center. Cells inside and around it release molecules that attract repair cells. New blood vessels begin to grow toward the damaged area. This is called angiogenesis, the formation of new blood vessels. It is essential because healing tissue needs oxygen, nutrients, waste removal, and a supply route for repair cells. So the first hours and days after a fracture are preparation. The body stops the bleeding, creates inflammation, cleans damaged tissue, restores blood supply, and prepares the fracture site for the next stage. But the next tissue is not hard bone yet. It is softer, more flexible, and temporary. This bridge is called the soft callus. Granulation tissue and the soft callus. After the first inflammatory response, the fracture area begins to change. The hematoma is gradually replaced by granulation tissue. Granulation tissue is soft, living repair tissue. It contains small new blood vessels, immune cells, and early repair cells. It prepares the fracture site for new tissue formation. This transition is essential because the body cannot jump directly from a blood clot to strong bone. It must first create a soft biological bridge. As new blood vessels grow into the granulation tissue, special repair cells gather around the fracture. Some of the most important are mesenchymal stem cells. These are flexible repair cells that can develop into different types of tissue depending on the signals around them. In fracture healing, many of these cells come from the periosteum and the endosteum. The periosteum covers the outside of the bone. The endosteum lines the inner surface of the bone. Both help provide cells for repair. Under the right conditions, mesenchymal stem cells can become cells that produce cartilage-like tissue, or cells that help form new bone. This is where the body starts forming a soft callus. A soft callus is a temporary repair structure made mainly of collagen, fibrous tissue, and cartilage-like tissue. Its purpose is not to make the bone fully strong. Its purpose is to connect the broken ends and reduce movement between them. Think of it as the body's first internal splint. It is weaker than mature bone, but it gives the fracture early stability. Still, the soft callus cannot safely handle full weight or heavy pressure. That is why medical stabilization is important. A cast, splint, plate, screw, or external fixator does not create the bone. The body creates the bone. But stabilization keeps the broken pieces in a better position while the body works. The fracture site changes from a damaged, bleeding zone into an organized healing structure. To restore strength, it must harden that bridge. It must replace the cartilage-like tissue with immature bone. This process is called endochondral ossification. Endochondral ossification means that cartilage is gradually transformed into bone. And this brings us to the hard callus. The hard callus. The soft callus connects the broken ends, but it is not strong enough to carry normal force, so the body begins hard callus formation. Inside the repair zone, the cartilage-like tissue of the soft callus is gradually replaced by immature bone. This is the moment when the body moves from temporary repair to structural repair. Cells called osteoblasts become highly active. Osteoblasts are bone-forming cells. Their job is to produce new bone matrix, the material that will later become mineralized and hard. At first, this new bone is not perfectly organized. It is called woven bone. Woven bone is immature bone. It forms quickly, helps bridge the fracture, and gives the damaged area more strength. But it is not as organized or as strong as mature bone, so woven bone is created as emergency repair material. Not perfect, but strong enough to begin restoring support. As the hard callus grows, the fracture becomes more stable. The broken ends are now connected by a harder, mineralized bridge. This does not mean the bone is fully healed, but it means the body has moved into a new phase. Minerals, especially calcium and phosphate, are deposited into the new bone matrix. This process is called mineralization. Mineralization gives bone its hardness. Bone strength comes from both collagen for flexibility and minerals for hardness. But the repair is still not complete. The new bone is irregular. The callus may be larger than the original bone shape. The internal structure is still disorganized, and the fracture line may still be visible for some time. This is why healing takes weeks to months, depending on the bone, fracture type, blood supply, age, health, nutrition, and stability. The fracture is becoming one structure again, but the new structure is still rough. It still needs shaping, strengthening, and remodeling. Bone remodeling. The hard callus gives the fracture strength, but it is not the final version of the bone. Now the body must refine the repair. This stage is called bone remodeling. Bone remodeling is the process where immature bone is slowly reshaped into stronger, more organized bone. The body begins replacing woven bone with lamellar bone. Woven bone forms quickly, but its structure is random and irregular. Lamellar bone is more organized, stronger, and better adapted to mechanical stress. This transformation can continue for months. In some cases, remodeling can continue for years. Osteoclasts remove bone. Osteoblasts build bone. Because the first hard callus is not perfectly shaped, the body must reshape it. It may contain extra bone. It may be too wide or uneven. It may not follow the original architecture of the bone, so osteoclasts resorb parts of the callus. They break down bone tissue in controlled areas, remove excess material, and help reshape the structure. Then osteoblasts follow. They deposit new bone matrix and rebuild stronger, more organized bone. This balance is called coupled remodeling. Together, osteoclasts and osteoblasts slowly turn the hard callus into mature bone. Bone also responds to mechanical forces. Areas that experience useful stress can become stronger. Areas that are not needed may be reduced. This principle is often connected with Wolff's Law, the idea that bone adapts to the loads placed upon it. But this does not mean someone should stress a fracture too early. That is why doctors control when a person can start moving, putting weight on the limb, or doing rehabilitation. During remodeling, the fracture line slowly becomes less visible. The bulky callus becomes smoother. The internal canal of the bone, called the medullary canal, may be restored. The outer shape becomes closer to its original form. Even when an X-ray looks improved, the biological process may still be continuing. Bone healing is not one event. It is a sequence: hematoma, inflammation, granulation tissue, soft callus, hard callus, remodeling. But not every fracture heals perfectly. When a fracture takes longer than expected to heal, it is called a delayed union. When a broken bone fails to heal, it is called a non-union. And when a bone heals in the wrong position, it is called a malunion. These complications remind us that bone healing is powerful, but not automatic. The body needs the right conditions: blood supply, oxygen, nutrients, repair cells, stability, and good alignment. Why some bones do not heal properly. Bone is living tissue. Without blood, repair cells cannot arrive properly. Oxygen cannot reach the healing zone. Waste cannot be cleared efficiently. New tissue cannot form well. If the fracture is severe, crushed, or open, the biological environment becomes more complicated. An open fracture is when the broken bone communicates with the outside environment through a wound. This increases the risk of infection, and infection can seriously interfere with healing. Instead of focusing only on rebuilding bone, the body must also fight invading microorganisms. Another major factor is stability. If there is too much movement at the fracture site, the soft callus can be disturbed, and the body may struggle to turn temporary tissue into strong bone. This is why casts, splints, plates, screws, rods, or external fixators are used. They do not replace biology, they support biology. They hold the bone in a better position so the body can repair it. Alignment also matters. If bone fragments are too far apart, badly rotated, or trapped in the wrong position, the body may not bridge the gap correctly. But the condition of the whole body also matters. Smoking can slow bone healing because it affects circulation, oxygen delivery, and cellular repair. Diabetes can increase the risk of healing complications because it can affect blood vessels, inflammation, immunity, and tissue repair. Poor nutrition can also interfere with healing. The body cannot build new tissue from nothing. It needs protein, energy, minerals, and vitamins. Age can also influence healing. Children often heal faster because their bones are still growing and their biology is very active. Older adults may heal more slowly, especially if they have osteoporosis, reduced blood supply, chronic disease, or lower regenerative capacity. Modern medicine works with the body's healing system. A cast gives stability. Surgery can restore alignment. Plates and screws can hold fragments together. Antibiotics may be needed when infection is a risk. Rehabilitation can help restore movement and strength at the right time. But even with all of this, the final healing still comes from living tissue. A doctor can align the bone, a cast can protect it, a plate can hold it. But the body must do the healing. Inside the body, a fracture is not only destruction, it is the beginning of repair. Blood vessels tear, but blood forms a hematoma. Inflammation begins, but inflammation brings immune cells and repair signals. Granulation tissue forms, new blood vessels grow. Mesenchymal stem cells arrive. A soft callus bridges the fracture. The body hardens that bridge. Osteoblasts build new bone. Minerals strengthen the matrix. Woven bone appears. Then remodeling begins. Osteoclasts remove what is unnecessary. Osteoblasts rebuild what is needed. The body does not just glue the bone together. It builds a temporary scaffold. It creates a blood supply. It sends immune cells. It recruits repair cells. It lays down collagen. It mineralizes new tissue. It reshapes the repair according to force. It turns a damaged fracture site into living architecture again. Your body does this quietly, cell by cell, signal by signal, day by day. A fracture may take seconds to happen, but healing takes time. Weeks for the first strong repair, months for remodeling, sometimes even longer for the bone to fully adapt. Your skeleton is not dead material, it is alive. It can bleed, it can hurt, it can grow, it can adapt, it can repair. Your bones are living organs. Damage is not always the end. Sometimes damage is the signal that begins reconstruction. A broken bone begins as pain, then blood, then inflammation, then soft tissue, then new bone, then remodeling, and finally, strength. The crack becomes a callus. The callus becomes bone. The bone becomes structure, and the structure becomes part of you again. So the next time you see an X-ray of a fracture, remember what is happening beneath the image. Not just a broken line, not just a medical case, not just a damaged skeleton, but millions of cells answering one question: how do we rebuild what was broken? And inside you, the answer begins immediately. This is Innerium, the science inside you.